Last week, we learned how to manipulate bits in a computer. We have yes, we have no, 1, 0, and we know how to manipulate them. But what can we do only with 1 and 0? Can we represent more sophisticated things with them? Of course, we must if we want to use our computer to do useful things. But what can you do with only two values, 0 and 1? Well, you definitely can put two of them together, and then you get 4 possibilities. 3 of them together, you get 8 possibilities. In general, if you have n of them together, you have 2 to the n possibilities. And now you can represent any 2 to the n different things that you may want to. For example, you can represent numbers. And this is what we're going to be interested in. How are you going to represent integer numbers? Well, 0 is easy. 0, 1 is easy, 1. 2 is already the first problem, basically because we don't have yet another possibility, so we have to use 2 bits, 0, 1, 0. 3 is 1, 1. For the next one, we already need another bit, 1, 0, 0, 4, 4. And in general, it seems we can represent any numbers that we want with some sequence of bits. Now, how did we connect the sequence of bits, the binary representation of an integer number, to the integer number? What's going on? What's the general system? In order to understand that, we have to go back to 2nd grade, when we learned about decimal numbers. We see 789. What does that mean? What does the digits 7, 8, and 9 have to do with the value of the number 789? Well, we learned that we have the positional system, where the rightmost digit is the ones, the next one is the tens, the next one is the hundreds. So we know that 789 is really 9 plus 8 tens plus 7 100s, and so on. In general, the case position from the right is 10 to the k. So now exactly the same thing is going to happen also with binary numbers, but it's going to be much simpler because we only have 0 and 1 rather than all the digits between 0 and 9. Thus, in binary notation, the different positions will be powers of 2. 1, 2, 4, 8, and so on. Suppose you want to know, for example, what is the value of 101 in binary notation. Well, we know the rightmost bit is basically the 1s. The next one, the 0, corresponds to 2s. And the third, the leftmost bit here, is the 4s. Altogether, we have 4 plus 2 times 0 plus 1 times 1. Altogether, that's 5. So our number is 5. And in general, what do we do in general? Exactly the same thing. You have any sequence of bits, and we're going to number them from the rightmost bit, which is going to be b0, the next one b1, and so on, all the way to bn, if we have n plus 1 bits. And the value of this thing is going to be b0 times 2 to the 0, plus b1 times 2 to the 1, plus b2 times 2 to the 2, all the way until the nth bit, which we have, where we have bn times 2 to the n. And this is going to be a number. And that's how we can convert any sequence of bits, any binary representation of a number, to the value of a number. One thing that we should note at this point, that if we look at the maximum number we can represent with k bits, well, we sum up from 2 to the 0 all the way to 2 to the k minus 1. Remember that the kth bit, if we start counting from 0, the last bit is counted, is indexed to k minus 1. So we have the sum of 1 plus 2 plus 4 all the way to 2 to the k minus 1. Altogether, we have 2 to the k, all that minus 1. And that's the range of bits we can actually represent with k, the range of numbers we can represent with k bits. Now, so far we assumed we have an arbitrary length number of bits that we can use to represent. And of course, if we want to represent an arbitrary long number, we will need an arbitrary number of bits. In computers, you usually have a fixed number of bits that is allocated. And then, of course, you will only be able to represent a fixed range of the integer numbers. So, for example, if we only have 8 bits, what are the possible numbers you can represent? Well, you can represent something starting with 0, 0, 0 8 times, 0, 0, 0 and ending with a 1, all the way up to 8 ones. The smallest number is, we have altogether 256 such possibilities. The first one is indexed 0, the last one is indexed 255. Now that's not exactly true. Really, when we have 8 bits, usually we want to reserve part of all the possibilities to actually represent negative numbers. We're not going to actually talk about this now, but rather a unit from now. But in general, half of the 256 possibilities are going to be reserved for negative numbers, and we're only going to be able to use the numbers between 0 and 127, and these are the positive numbers that we're going to be able to use out of these 256 possibilities of 8 bits. So far we saw, basically, if you get a string of bits, how can you convert it to decimal numbers? Now we're going to do the opposite thing. Suppose you're given a number in decimal, 87 for example. How can you represent it as a sequence of bits? This is also something that we should be able to do if we're going back and forth between decimal notation and binary numbers that are actually going to be represented in the computer. Well, remember that we know that really the way we get the decimal from the binary is by summing up powers of 2. So we start by figuring out what is the largest power of 2 that fits into our 87 number, and that is going to be 64. And then what is the next one? After we have 64, what is the next power of 2 that we can add to 64 and we still remain under 87? That turns out to be 16. And so on, we can keep on going, and we write the number 87 as a sum of powers of 2. And it turns out that 87 is exactly 64 plus 16 plus 4 plus 2 plus 1. And once we have that, from this representation of the decimal number as a sum of powers of 2, we can quite directly actually get the binary representation. How do you do it? Well, every time we have a power that appears in the sum, we need to put a 1 in the bit there. And whenever the power is not part of the sum, we put a 0 there. So for example, look at the rightmost bit. That corresponds to the 1s. We do have a 1, so that's going to be a 1. On the other hand, if you look at the third bit from the right, which corresponds to the 8s, since we don't have 8 in our sum here, we're going to have 0 there. And that's basically a general way how you can take any number and convert it to binary. So this concludes this unit, where basically we discussed how you can represent integer numbers in a binary system. In the next unit, we're going to actually discuss how can we actually perform arithmetic operations, in particular addition, on these represented binary numbers. Once we get that under our belt, we will go back and discuss the issue of negative numbers in Unit 3.